Deep within the frozen, silent darkness of the constellation Ursa Minor, something is haunting our most advanced telescopes, a ghost that simply refuses to die. According to every single law of astrophysics we have ever written, the planet known to us as Hala should not exist in this universe. This is not just a scientific anomaly. It is a direct violation of the fundamental rules that hold our reality together. The planet orbits a star named Baekdu, a celestial body that has already entered the violent final stages of its life cycle. We know for a fact that this star expanded into a massive red giant, swelling outward to swallow everything in its path. Mathematical models confirm that the star's radius extended well beyond the orbit of the planet, engulfing it in an ocean of fire. By all accounts, Hala should have been incinerated, ripped apart by tidal forces, and reduced to absolutely nothing but scattered atomic ash. Yet, when astronomers at the Mauna Kea Observatory looked at the data, the planet was still there, silently mocking our understanding of death. It is a zombie world, a survivor of a cosmic apocalypse that should have erased it from the history of the galaxy. If this planet can survive being swallowed by its own sun, then everything we predict about the end of our own world might be wrong. We are forced to ask a terrifying question. Are the laws of physics constant, or do they break when we aren't looking? The existence of 8 Ursae Minoris b suggests that we are missing a massive piece of the puzzle regarding how stellar systems evolve. Imagine standing on the surface of that world, looking up at a star that tried to eat you and somehow failed to finish the meal. The temperatures would have been hot enough to boil rock, yet the planet remains intact, holding onto its mass against all odds. Astronomer Mark Hahn and his team were initially convinced the data was a glitch, a ghost in the machine of the TESS telescope. But repeated observations confirmed the impossible. The rhythmic gravitational tug of a planet that is theoretically dead was very much alive. This discovery forces us to rewrite the textbooks on planetary engulfment and consider violent alternative histories for this star system. One theory suggests a cosmic crime scene involving a second star, a hidden accomplice that altered the fate of the entire system. If the star Baekdu was once a binary system, 2 stars might have merged together before the planet could be fully consumed. This merger would have halted the expansion of the red giant, a stellar sacrifice that inadvertently saved the doomed planet from destruction. But even this explanation requires a sequence of events so precise and rare that it feels less like science and more like divine intervention. We usually find comfort in the predictability of the cosmos, in the knowledge that gravity and thermodynamics are absolute rulers. Hala destroys that comfort, proving that out in the darkness, there are exceptions that can defy the inevitable heat death of a world. This is not the only anomaly. The universe is littered with forbidden planets that exist in zones where formation should be impossible. Consider the implication for Earth. We believe our sun will eventually expand and consume us, erasing all evidence of humanity. If a planet can survive that fiery fate, perhaps the end of the solar system is not as written in stone as we thought. However, survival came at a cost. The planet Hala is likely a scorched, irradiated wasteland, a monument to cosmic trauma. It serves as a grim reminder that survival in this hostile universe does not necessarily mean life, only the persistence of matter. The atoms in your own body were forged in stars that died, and perhaps, like Hala, we are all just leftovers of a violent past. As we gaze deeper into the abyss, we are finding more objects that challenge the standard model of planetary formation. From hot Jupiters orbiting impossibly close to their hosts, to rogue planets wandering the void without a sun to call home. Every time we open a new door with instruments like James Webb or TESS, we find something that scares the established scientific community. It is a humbling realization that our map of the universe is still mostly blank, filled with monsters we have yet to name. The planet Hala is 520 light-years away, meaning the light we see today left that world before the telescope was even invented. We are looking back in time at a crime scene, trying to reconstruct the murder of a star and the survival of its victim. The universe does not care about our theories. It creates what it wants, even if that creation violates our logic. We are drifting through a chaotic ocean where the waves are made of gravity and the storms can last for billions of years. To understand Hala is to understand that we are not safe, that the stability of our solar system is a fragile, temporary state. What other impossibilities are hiding in the data, camouflaged by our own arrogance and our assumption that we know the rules? There is a distinct possibility that our physics is merely a local approximation, valid here but broken elsewhere in the cosmos. The forbidden planet forces us to confront the unknown with humility, terror, and an insatiable need to uncover the truth. As we peel back the layers of this mystery, we must be prepared for the answer to be stranger than we can imagine. The survival of Hubble might involve exotic states of matter or gravitational interactions we have not yet discovered in our laboratories. We are like children playing with blocks, unaware that the house we are building is sitting on a fault line of reality. The investigation into 8 Ursae Minoris b is not just about a planet, it is about the limits of human knowledge. We are about to dive into the specifics of this anomaly, dissecting the light curves and the radial velocity data. The numbers tell a story of violence, resilience, and a narrow escape from the belly of a dying, expanding star. But be warned, once you accept that impossible planets exist, the night sky will never look quite the same to you again. We are entering the realm of the forbidden, where the impossible becomes inevitable and the dead do not always stay dead. Let us examine the evidence, the theories, and the chilling reality of the planet that cheated death itself. To truly understand the sheer impossibility of the world we call Hubble, we must first dismantle our comfortable, simplistic understanding of how a solar system functions and eventually dies. For centuries, the standard model of stellar evolution has been our Bible, a rigid set of commandments dictated by the laws of thermodynamics and nuclear physics that told us exactly how stars are born, how they live, and how they inevitably destroy their children. We look at our own sun as a benevolent life giver, a steady yellow dwarf that provides the warmth and energy necessary for our biological existence. But this stability is a temporary illusion, a fleeting moment of balance in a violent universe. Deep inside the core of every main sequence star, a war is being fought between the crushing inward weight of gravity and the explosive outward pressure of nuclear fusion, a delicate stalemate that holds the star together for billions of years. But this war cannot last forever, and when the fuel runs out, the truce is broken, leading to a catastrophic metamorphosis that should, by all logic, sterilize and consume the inner system entirely. The mechanics of this stellar death are well documented and mathematically precise. When a star like Bacdu exhausts the hydrogen fuel in its core, the hydrostatic equilibrium that kept it stable for eons suddenly collapses. The core, now deprived of the energy generation that supported it against its own weight, begins to shrink and heat up, driven by the relentless, crushing force of gravity that never sleeps. This contraction ignites a shell of hydrogen around the core, causing the outer layers of the star to expand drastically, bloating the star into a red giant, a monster that can grow to hundreds of times its original size. It is not merely a change in color or brightness, it is a physical expansion of the star's atmosphere into the orbital paths of its closest planets, a slow-motion tsunami of plasma that swallows everything in its vicinity. This is the fate that awaits our own Earth in roughly 5 billion years, a fiery execution where the sky itself descends to burn the ground we walk on. The star 8 Ursae Minoris, or Bacdu, is a star that has unequivocally reached this terminal phase of its existence, having burned through its primary fuel and swollen outward into the void. Astronomers classify it as a clump giant, a star that is currently fusing helium in its core, which means it has already passed through the maximum expansion of the red giant branch. We can rewind the clock using evolutionary tracks, complex computer simulations that reverse the physics of the star, to see exactly how large it grew in the past. The data is terrifyingly clear. At the peak of its expansion, Bacdu's radius would have extended out to a distance of roughly 0.7 astronomical units, or 70% of the distance between the Earth and the Sun. This calculates to a sphere of influence that is millions of miles wide, a zone of absolute destruction where no solid matter should be able to remain intact. This brings us to the anomaly, the logical fracture that keeps astronomers awake at night. The planet Hubble orbits Bacdu at a distance of only 0.46 astronomical units. Simple subtraction tells you the horrifying truth. The planet is currently sitting comfortably inside the radius that the star allegedly occupied just a few million years ago. It is orbiting deep within the kill zone, a region of space that was, by our best calculations, filled with the searing hot plasma of the star's atmosphere. Imagine a swimmer casually doing laps inside a volcano that has already erupted. That is the physical paradox we are observing. If the star expanded to 0.7 astronomical units, and the planet is at 0.46 astronomical units, the planet should have been engulfed, dragged down by friction, and vaporized into its constituent atoms. There is no orbit inside a star for a gas giant. The physics of drag and tidal forces dictate a swift, spiraling death. When a planet enters the atmosphere of an expanding star, it experiences a phenomenon known as orbital decay, which is a polite scientific term for a violent, irreversible death spiral. The tenuous gas of the star's outer envelope acts like a thick fluid, creating immense drag on the planet as it plows through the plasma at thousands of miles per hour. This friction steals energy from the planet's orbit, causing it to slow down and drop lower and lower into the star, spiraling inward toward the superheated core, where the temperatures are high enough to rip electrons from their nuclei. This process is usually rapid in cosmic terms, taking perhaps only a few centuries or millennia, meaning that once a planet is engulfed, it does not come back out. It becomes fuel, it adds its mass to the star and ceases to exist as a distinct object. Halla surviving this process is akin to a drop of water surviving inside a blast furnace. The discovery was first flagged by the Transiting Exoplanet Survey Satellite, or TESS, a space telescope designed to hunt for the faint shadows of worlds crossing in front of their host stars. TESS detected a rhythmic dimming of Bakdu's light, a heartbeat that suggested something was obstructing our view at regular intervals. But a simple transit signal is not enough to claim a discovery of this magnitude. Transits can be faked by background stars, instrumental glitches, or even star spots on the rotating surface of the giant itself. The team needed to confirm that the object had mass, that it was a physical body tugging on the star and not just a trick of the light. They turned to ground-based observatories in Hawaii to use the radial velocity method, a technique that measures the wobble of a star as it is pulled back and forth by the gravity of an orbiting planet. The radial velocity data from the W.M. Keck Observatory was unambiguous and chillingly precise. The star Bakdu was indeed wobbling, pulled by an unseen companion with a mass roughly 1.5 times that of Jupiter. The periodicity of the wobble matched the transit data perfectly, locking in the orbital period at approximately 93 days. This was the smoking gun, the confirmation that a massive planetary body was circling this dying star at a distance less than half the distance from Earth to the Sun. The numbers were checked, rechecked, and checked again because the implication was simply too bizarre to accept immediately. The planet was real, the orbit was real, the star was real. But the timeline of history required for all three to exist simultaneously was impossible under the standard model of single-star evolution. We are forced to consider the specific dynamics of the system. Halla is a gas giant, a hot Jupiter-type planet, but unlike others of its kind, it is not just hot, it is a survivor of a thermal holocaust. If it had been engulfed, even for a short period, the outer layers of the planet, the hydrogen and helium atmosphere, would have been stripped away by the intense heat and the solar wind, leaving behind only a scorched rocky core, a Chthonian planet. Yet, the mass measurements suggest Halla is still a gas giant, retaining its thick, volatile atmosphere. This implies that it never actually touched the star's envelope, that the star somehow stopped expanding right before it consumed the planet, or the planet was never in that position to begin with. Both scenarios require us to invent new physics or discover a hidden history that has been erased from the system. Let us delve into the binary merger theory, which is currently the leading explanation for this cosmic ghost story. Though it paints a picture of celestial cannibalism, most stars in the Milky Way are not solitary wanderers like our Sun. They are born in pairs, locked in a gravitational dance with a binary partner. If Bakdu was originally two stars orbiting close to one another, their evolution would have been radically different from a single star. As the primary star began to expand into a red giant, it would have started to dump its mass onto its smaller companion, altering the balance of the entire system. Eventually, the expansion of the primary star would have enveloped the smaller star, creating a common envelope phase where two stellar cores spiral around each other inside a single, massive cloud of gas. In this violent merger scenario, the two stars would eventually spiral together and collide, fusing into a single new object, the star we now see as Bakdu. This merger is the key to the mystery, because the energy released and the mass ejected during the coalescence would have halted the expansion of the red giant early. The star would have burped out its outer layers before they could expand far enough to reach the orbit of Halla. In essence, the death of the second star saved the planet. The smaller star was sacrificed, consumed by its larger sibling, to prevent the red giant from growing to its full planet-killing size. Halla watched its parent stars eat each other, and because of that act of stellar fratricide, the planet was spared from the fire. This theory of a stellar merger explains why Baekdu is smaller than a typical red giant should be at this stage of burning helium, and it explains why Halla is still alive. But it transforms the system from a standard planetary model into a graveyard of a binary system. It suggests that what we are looking at is a reborn star, a Frankenstein's monster stitched together from the corpses of two previous stars. The planet orbits a star that is chemically and physically different from the one it was born around. The gravitational dynamics, the radiation output, the magnetic fields, everything changed the moment the two stars merged. Halla is an orphan that was adopted by the monster that ate its parents, orbiting in a stable path around a tumultuous, fused core. However, there is a darker, alternate theory that we must consider: the possibility that Halla is a second-generation planet, a world born from the ashes of the dead. In this scenario, the original planets of the system were indeed destroyed, engulfed, and vaporized when the red giant expanded. The debris from this destruction, the gas, the dust, the pulverized rock of the former worlds, would have formed a massive accretion disk around the star. From this disk of death, a new planet could have coalesced, rising like a phoenix from the remains of its predecessors. If this is true, then Halla is not a survivor. It is a new creation, built from the recycled atoms of the planets that died before it. It is a world made of ghosts. The implications of second-generation planet formation are profound because they suggest that solar systems can reincarnate, that the death of a star is not the end of planetary formation but a new beginning. But this process requires an immense amount of material and a stability that is hard to maintain around a dying star. The time frame for a planet to form from a debris disk is typically millions of years, yet the red giant phase is relatively short and turbulent. Could a gas giant as massive as Jupiter really assemble itself that quickly in such a chaotic environment? Or is this theory just our desperate attempt to fit a square peg into a round hole because the reality of the situation, that a planet simply refused to die, is too unsettling for us to accept? We must also look at the chemical composition of the star Baekdu, specifically its abundance of lithium, an element that is usually destroyed in stars as they age. High concentrations of lithium in a red giant are often considered a sign of recent engulfment, a chemical burp caused by eating a planet or a brown dwarf. If Baekdu has an unusual amount of lithium, which some data suggests, it might indicate that it did eat something. Perhaps there were other planets closer in, brothers and sisters of Halla, that did not escape the expansion. Halla might be the sole survivor of a massacre, the outermost child that watched its siblings disappear into the encroaching wall of fire. The silence of that system is the silence of a battlefield after the war is over. The sheer scale of these forces is impossible to grasp from the human perspective. We are talking about a star with a mass equivalent to hundreds of thousands of Earths, swelling to a size where it could contain millions of suns. The energy output during the helium flash, the moment the core ignites helium fusion, is brief but cataclysmic, releasing more energy in seconds than our galaxy produces in years. For a planet to be sitting in the front row of such an event and remain gravitationally bound and physically intact is a testament to the resilience of angular momentum. It reminds us that gravity is the ultimate arbiter of the cosmos. It builds stars, it crushes them, and occasionally it creates pockets of stability in the midst of absolute chaos. But why does this matter to us, sitting here on our small blue rock, thousands of light years away? Because Halla is a mirror reflecting a possible future for our own solar system. We have long assumed that when the Sun expands, Mercury and Venus are doomed, and Earth sits on the razor's edge of survival. The discovery of Halla suggests that the line between survival and destruction is blurrier than we thought. If a planet can survive at 0.46 astronomical units around a burning giant, perhaps Earth could survive the Sun's death throes. Or, conversely, perhaps the violence of our Sun's future is far more complex and unpredictable than our linear models suggest. We are forecasting the weather of the apocalypse based on a sample size that is terrifyingly small. The study of 8 Ursae Minoris b is a stark lesson in survivorship bias. We look at the universe and see the planets that survived, the stars that stabilized, the galaxies that held together. We do not see the trillions of worlds that were swallowed, the systems that were torn apart, the failures of cosmic evolution. Hala is the exception that proves the rule, a rare statistical outlier that managed to thread the needle of extinction. It stands as a lonely beacon in the Ursa Minor constellation, signaling that while the universe is a machine of destruction, it is also a machine of chance. And sometimes, against all probability, the dice roll in favor of existence. There is an existential horror in looking at Hala's orbit, a perfect circle drawn around a dying heart. A circular orbit usually implies age and stability, a system that has settled down over eons. If Hala had been disturbed by a merger or a violent event, its orbit should be eccentric, an elongated oval swinging wildly in and out. But the orbit is nearly circular, which deepens the mystery. How did it maintain such perfect composure while the star specifically underwent a binary merger or a massive expansion event? It is as if the planet was protected by a bubble of calm while the rest of the system burned. This dynamic tranquility in the face of stellar violence is perhaps the most puzzling aspect of the entire discovery. Let us zoom in on the star Baekdu itself, a spectral-type K-giant. To the human eye, it would appear as an intense, orange-red orb looming massive in Hala's sky, occupying a terrifying portion of the celestial dome. The light hitting the planet is shifted towards the infrared, a heat that bathes the cloud tops of the gas giant in perpetual, searing twilight. There are no days or nights as we know them. There is only the relentless gaze of the giant. The radiation pressure alone would be stripping away the upper atmosphere, creating a comet-like tail of gas trailing behind the planet, a bleeding wound in the sky that marks its path through the stellar wind. The resilience of Hala challenges our definitions of habitable versus survivable. While certainly not habitable for life as we know it, the planet's existence suggests that the architecture of planetary systems is far more robust than we give it credit for. It implies that planets are not fragile ornaments but sturdy gravitational anchors. However, this robustness is a double-edged sword. If planets can survive in such extreme environments, it means the universe is populated with tortured worlds, planets that are locked in agonizingly close orbits to dying stars, baked by radiation, stripped of their protective layers, yet unable to die. It is a gallery of cosmic horrors where existence is a punishment. As we analyze the light curve data from TESS, we look for transit timing variations, tiny discrepancies in the timing of the planet's orbit that would indicate the presence of other unseen bodies. So far, Hala appears to be alone, a solitary traveler. The lack of companions is significant. In many planetary systems, the gravitational interplay between multiple planets can eject one into deep space or push one into the star. If Hala had siblings, they might have been the victims of such a scattering event, sacrificed to the void so that Hala could secure its stable circular orbit. The stability we see today may be the result of a violent dynamical instability in the past that cleared the board of all other players. The helium flash that Baekdu underwent is a critical moment in this narrative. When the hydrogen shell burning adds enough mass to the helium core, the core becomes degenerate, a state where quantum mechanics, not thermal pressure, supports the star. Eventually, the temperature rises until the helium ignites explosively. This event happens deep inside the star and is not immediately visible on the surface, but it restructures the entire interior of the star. For a planet orbiting nearby, this internal restructuring changes the gravitational field it moves through. The fact that Hala remained bound to the star during this gravitational shudder is another stroke of immense luck, or a sign of physics we have yet to model correctly. We must also consider the role of tidal locking. At this close distance, Hala is almost certainly tidally locked to Baekdu, meaning one side of the planet permanently faces the star, while the other faces the frozen darkness of space. The day side is a roasting hellscape bombarded by the fierce winds of the red giant, while the night side is a realm of eternal shadow. This temperature gradient creates supersonic winds that scream around the planet, carrying heat from the day side to the night side. The weather on Hala would be apocalyptic. with storms larger than Earth raging for centuries, driven by the desperate need of the atmosphere to equalize the impossible difference between fire and ice. The scientific community is currently divided, caught between the merger hypothesis and the survival hypothesis. The merger hypothesis is cleaner, mathematically speaking. It solves the radius problem by preventing the star from getting too big. But it relies on the existence of a hypothetical second star that we can no longer see because it has been eaten. It is a convenient solution, blaming the ghost of a dead star to explain the living planet. The survival hypothesis is messier. It requires the planet to endure forces that should have destroyed it. It forces us to question our calculations of stellar radii and tidal friction. In science, we usually prefer the simplest explanation, but in this case, both explanations are extraordinarily complex and violent. If we accept the merger theory, we are accepting that binary stars can essentially reboot their evolution. This has profound consequences for the search for life. If a binary merger can halt the expansion of a red giant, it creates a period of stability, a second wind, where life could potentially emerge or persist on outer planets. It means that the Goldilocks zone of a star is not fixed. It can move, shift, and be reset by cosmic collisions. It widens the search field for exoplanets, telling us to look not just at stable, boring stars, but at the messy, merged survivors of stellar combat. But let us not forget the third, darker option, that our understanding of gravity at these scales is flawed. We rely on general relativity to predict these orbits, but we know relativity breaks down at certain extremes. While a planetary orbit is hardly a quantum singularity, the precise interaction between a gas giant and a diffuse, expanding stellar envelope involves fluid dynamics, gravity, and magnetohydrodynamics all acting at once. We are modeling this with approximations. It is possible that the drag forces inside a stellar atmosphere are not as strong as we think, or that the density of the red giant's outer layers is much lower than predicted. We might be overestimating the lethality of a star. This brings us back to the concept of the Roche limit. This is the distance within which a celestial body, held together only by its own gravity, will disintegrate due to a second celestial body's tidal forces exceeding the first body's gravitational self-attraction. Hela is dangerously close to this limit. As the star expands, its gravity pulls harder on the front of the planet than the back, stretching it into a football shape. If it crosses the line, the planet simply breaks apart, turning into a ring system of dust and rock. Hela is tiptoeing on the edge of this gravitational cliff, holding itself together against the desire of the star to rip it into pieces. The discovery of Hela was published in the journal Nature, the gold standard of scientific verification, which means this is not a fringe theory from a dark corner of the internet. It has withstood the scrutiny of the world's best astrophysicists, and they are still scratching their heads. The paper essentially concludes with a shrug, offering the merger theory as the best guess but admitting that the system is a profound anomaly. It is a humbling moment for science when the data simply points a finger at our models and says, "You are wrong." It reminds us that the universe is under no obligation to make sense to us. As we stare at the visuals of this system, visualize the vast emptiness of the cosmos that surrounds it. This drama is playing out in a tiny pocket of warmth 520 light-years away, surrounded by the crushing cold of the interstellar medium. The isolation of Hela is total. There are no neighbors, no other planets detected so far, just this one survivor and its dying master. It is a closed loop of interaction, a solitary confinement cell made of gravity. The psychological horror of such isolation, if one were to personify the planet, is absolute. It is the last witness to the history of its system. The instruments we use to detect this, the spectrographs measuring the Doppler shift of the light, are sensitive enough to detect a star moving at the speed of a brisk walk. We are measuring the heartbeat of a star light-years away to the meter per second. This precision is what allows us to be certain of the planet's presence. We can see the star lurching back and forth as Hela swings around it. It is a gravitational tug-of-war, and while the star is winning by sheer mass, the planet is pulling back just enough to make its presence felt. It is a subtle, invisible dance revealed only by the splitting of light into its component colors. What if Hela is not a gas giant, but a failed star, a brown dwarf? The boundary between a massive planet and a brown dwarf is around 13 Jupiter masses. Hela is estimated at 1.6 Jupiter masses, placing it firmly in the planetary regime. However, if it had started as a brown dwarf and lost mass during the star's expansion, it could be a stripped core of something much larger. This evaporation scenario would mean we are looking at the withered husk of a once mighty celestial body. It adds another layer of decay to the system. A dying star orbited by a dying substar, both fading into the long night of the universe. The forbidden nature of Hala is what makes it so seductive to researchers. In astronomy, forbidden usually refers to quantum transitions that shouldn't happen but do under rare conditions. Here, it refers to a macroscopic object that defies the exclusion zones we have drawn on our maps. It is akin to finding a flower blooming in the middle of a nuclear blast crater. It forces us to redraw the maps. We now have to mark the engulfment zone of red giants not as a solid wall of death, but as a permeable barrier where, under the right circumstances, miracles can occur. Future observations with the James Webb Space Telescope could potentially analyze the atmosphere of Hala directly, looking for the chemical signatures of the star it orbits. If we find elements in the planet's atmosphere that match the enriched material of the red giant, it would confirm that the planet plowed through the star's outer layers and swept up the gas like a cosmic vacuum cleaner. This accretion of stellar material would be the final proof that the planet has indeed been inside the belly of the beast and emerged on the other side. It would be carrying the DNA of the star in its own sky. But until we get that data, we are left with the models and the mystery. The planet Hala stands as a monument to the unexpected. It challenges the linearity of time and stellar evolution. We tend to think of time as a straight arrow: birth, main sequence, red giant, white dwarf. But here, time seems to have looped or skipped a beat. The binary merger effectively wound back the clock for the star, buying it a second youth, while the planet simply waited out the chaos. It is a disruption of the temporal order of the cosmos, a glitch in the timeline of Ursa Minor. We must also consider the magnetic interaction between the star and the planet. A red giant has a deep, convective envelope that generates powerful magnetic fields. A close-in giant planet would interact with these fields, potentially acting as a dynamo that heats the star's atmosphere or triggers massive flares. This magnetic tether could transfer energy between the two bodies, locking them in a deadly embrace that slowly drains the orbital energy of the planet. Even if Hala survived the expansion, it might be doomed to spiral in eventually due to magnetic braking. Its survival might be temporary, a stay of execution rather than a pardon. The story of Hala is also a story of our own technological evolution. 20 years ago, we could not have found this planet. The dip in light is too small for ground telescopes to track reliably over long periods without the precision of space-based photometry like TESS. We are only now building the eyes sharp enough to see the monsters hiding in the dark. As our vision improves, the universe gets stranger. It suggests that the weird stuff is actually the norm, and our solar system, with its orderly, circular orbits and distinct spacing, might be the true anomaly. We might be the freaks of the galaxy. Think of the sheer emptiness of the space between the star and the planet. 0.46 astronomical units is roughly 42 million miles. It sounds like a lot, but on a cosmic scale it is intimate. The solar wind from Bayektu would traverse that distance in hours, slamming into Hala with the force of an unending gale. The charged particles would strip hydrogen from the planet, creating a cloud of neutral hydrogen gas that surrounds the system. If we could see in ultraviolet light, the entire system might look like a giant, glowing amoeba, with the star at the center and the planet embedded in its extended atmosphere. The concept of planetary engulfment is one of the most violent events in nature. The energy released when a planet plunges into a star can cause the star to brighten significantly for a few weeks. A red nova. If Hala had been consumed, civilizations across the galaxy might have seen Bayektu flare up briefly as it digested its meal. The fact that we see a steady light means the meal was refused. The star is hungry, it expanded its mouth, but the planet refused to be eaten. It is a defiance of the cosmic food chain. There is a terrifying beauty in the idea of the forbidden planet. It suggests that nature has a loophole for everything, even death. But loops are dangerous. They imply instability. If Hala exists where it shouldn't, what holds it there? Is it a delicate balance of forces that could be upset by the slightest nudge? A passing asteroid, a fluctuation in the star's output, a gravitational resonance. Any of these could destabilize the system and send Hala plunging into the fire. It is living on borrowed time, and in the universe, the interest rate on borrowed time is always infinite. The core helium burning phase of Baekdu will last for about 100 million years. This is a blink of an eye in cosmic terms, but a vast eternity for a planet under siege. After this phase, the star will exhaust its helium and expand again, this time into an asymptotic giant branch star. This second expansion will be even larger and more violent than the first. Hala survived the first wave, but the second wave is coming. The tragedy of this system is that the planet's survival is almost certainly doomed. It survived the red giant phase only to face the asymptotic giant phase. It is a Greek tragedy written in the stars. The hero fights fate only to realize that fate always wins in the end. This inevitability of destruction brings us back to the philosophical core of our investigation. Why do we care so much about a rock that is going to melt? Because it represents the struggle against entropy. The universe is a slide towards disorder, towards cold, towards darkness. Structures like solar systems are temporary fortresses against this decay. Hala is a fortress that held out longer than it should have. It is a symbol of resistance, even if it eventually falls. The fact that it stood for so long against the crushing weight of stellar evolution is a victory for complexity over chaos. The data from Hala also forces us to reevaluate the history of our own galaxy. How many merged stars are out there? If binary mergers are common enough to save planets like Hala, then the Milky Way might be full of these reborn systems. It would mean that stellar evolution is not a straight line, but a branching tree of possibilities, where stars can combine, reset, and change their destiny. The history of the galaxy is not a smooth narrative, but a series of violent collisions and revisions. As we move deeper into the analysis, we must keep in mind the limitations of our perspective. We are observing this system from one angle, at one specific moment in time. We see a snapshot of a movie that has been running for billions of years. We might be missing the context. Maybe Hala was captured from interstellar space recently. Maybe it formed further out and migrated in after the star shrank back down. There are migration scenarios where planets drift inward due to interactions with a disk. While less likely than the merger theory, we cannot rule out that Hala is a recent immigrant to the inner system, unaware of the danger it has moved into. The mystery of 8 Ursae Minoris b is a puzzle with missing pieces, and the pieces we do have don't fit the box cover. We have a star that is too small for its age, a planet that is too close for its survival, and an orbit that is too circular for its history. It is a trifecta of impossibilities. Each one alone could be explained away, but together they form a riddle that challenges the very foundations of planetary science. It is exactly the kind of anomaly that leads to breakthroughs. When the universe breaks the rules, it is trying to teach us new ones. We are standing on the precipice of a new understanding of stellar dynamics. The zombie planet Hala is our guide into the unknown. It beckons us to look closer at the dying stars, to search the graveyards of the galaxy for survivors. It tells us that life, or at least the planets that can support it, might be harder to kill than we thought. But it also warns us that the universe is a violent, churning place where safety is an illusion and survival is a statistical accident. In the next phase of our investigation, we need to look at the future of Hala. We know the star will expand again. We know the planet is running out of time. But what will the end look like? Will it be a sudden plunge or a slow evaporation? The study of this planet's death will be just as illuminating as the study of its survival. We are watching a slow-motion car crash that will take millions of years to resolve, and we are taking notes on the physics of the impact. The forbidden nature of this world serves as a checkpoint for our arrogance. We thought we had the life cycle of stars mapped out from cradle to grave. Hala proves we barely know the basics. It is a humbling correction from the cosmos. It says, "You have looked at the sky for a few thousand years and think you know the plot? You haven't even finished the opening credits." The arrogance of humanity is to assume that our local physics applies everywhere, unchanged and unbroken. So as we conclude this section of the inquiry, remember the image of Hala, a gas giant floating in the red glare of a swollen sun, a world that cheated death. It is a ghost in the machine, a glitch in the matrix of stellar evolution. It shouldn't be there, but it is. and its mere existence threatens to unravel everything we thought we knew about how solar systems die. It is the ultimate cosmic mystery, hiding in plain sight in the constellation of the Little Bear. But the story does not end with the planet. The star itself, Beidou, holds secrets in its core that we are only beginning to fathom. The helium burning process is unstable, prone to fluctuations that could send ripples through the star's structure. If we could listen to the star, using astroseismology, the study of starquakes, we might hear the internal churning of the merger that created it. The star is singing the song of its own violent past, and we are just learning how to tune in to the frequency. We leave Hubble, for now, suspended in its impossible orbit, a testament to the chaos of the universe. But the investigation opens up a wider question. If Hubble exists, what else is out there? What other impossible worlds are hiding in the glare of their dying stars? We are about to widen the net. We are about to look for the other survivors, the other ghosts, and what we find might be even more terrifying than a planet that refused to die. We might find worlds that never should have been born at all. To determine the true nature of the star Beidou, astronomers utilized a technique that borders on the metaphysical, astroseismology, the science of listening to the internal music of the stars. Just as geologists use earthquakes to map the interior of our planet, astronomers study the subtle, rhythmic brightness variations caused by sound waves bouncing around inside a star. These waves are trapped within the stellar interior, resonating at specific frequencies that depend entirely on the density, pressure, and composition of the gas they travel through. By analyzing these oscillations, we can effectively see inside the star, peeling back the blinding layers of the photosphere to reveal the nuclear engine hidden at the core. In the case of Beidou, the seismic data was unequivocal and damning. The frequencies detected matched the specific signature of a clump giant, a star that has already ignited helium in its core. This seismic fingerprint is the smoking gun that proves the star is not in its first youth. It is a post-expansion object that has already lived through its most violent growth phase. We are not guessing that the star expanded. The star's own internal vibrations are telling us that it did. This seismic confirmation forces us into a corner regarding the planet's survival. If the star were merely a young red giant on its first ascent up the expansion branch, we could argue that it simply hasn't grown large enough yet to eat the planet. But the clump status confirms that it has already peaked. It has already gone through the maximum radius phase where the hydrogen shell burning drives the outer layers into the void. This means the radius of the star must have exceeded the current orbit of the planet in the past, unless some external force intervened. The sound waves inside Beidou are singing a song of impossibility. They describe a history where the star grew large enough to consume its child, and yet the child is still there. It is like finding a house standing perfectly intact in the middle of a leveled city after a nuclear blast, with the seismographs confirming that the epicenter was right in the living room. The physics of the star and the physics of the orbit are in direct contradiction. Let us return to the merger hypothesis with a forensic eye, visualizing the sheer violence of such an event. Picture two stars, born together in a nebular nursery, orbiting each other for billions of years in a stable binary system. One is slightly more massive than the other, so it evolves faster, burning through its hydrogen fuel and beginning to swell. As it expands, it doesn't just grow into empty space, it grows into the gravitational territory of its partner. The outer layers of the dying giant begin to flow onto the smaller star, a vampiric transfer of mass that destabilizes the orbits of both. This is not a gentle process. It is a chaotic, turbulent interaction where the geometry of the system begins to collapse. Eventually, the smaller star is dragged inside the atmosphere of the larger one, entering the common envelope phase. Inside this churning cloud of superheated gas, the friction is immense. The orbital energy of the companion is converted into heat, spinning the envelope up and ejecting vast amounts of matter into deep space. This ejection of matter is the key to the planet's salvation in the merger scenario. As the two stars spiral together and merge, the energy released blasts the outer layers of the red giant away before they can expand to their full, planet-killing potential. It is a cosmic amputation. The star sacrifices its outer envelope to fuse with its companion. By shedding this mass, the star effectively shrinks, or rather fails to grow to the predicted size of a single star evolution. The planet Hala, orbiting at a safe distance from this central catastrophe, watches as its two suns become one. It survives because the merger event acted as a safety valve, releasing the pressure and preventing the star from swallowing the entire system. But this means Hala is orbiting a corpse made of two bodies, a merged star that hides the secret of its duality deep within a rapidly rotating core. The planet is a witness to a celestial murder-suicide pact that inadvertently saved its life. The concept of a common envelope evolution is usually discussed in the context of creating cataclysmic variables or supernovae, not saving planets. It highlights how little we understand about the interaction between binary stars and their planetary retainers. If this mechanism is common, it implies that the galaxy is filled with saved planets, worlds that owe their existence to the cannibalistic tendencies of their host stars. However, it also implies a chaotic environment. The ejection of the common envelope involves spewing trillions of tons of gas and dust into the system. Hala would have been bombarded by this material. Its atmosphere would have been pummeled by a stellar wind thousands of times stronger than anything we experience from the Sun. The planet might have gained mass from this debris, or it might have been stripped. It is a scarred survivor, likely bearing the chemical marks of that ancient explosion in its upper cloud layers today. This scenario offers no comfort to us here on Earth. Our Sun is a solitary star. It has no binary companion to merge with, no partner to sacrifice itself to halt the expansion. When the Sun enters its red giant phase in 5 billion years, there will be no common envelope event to save us. The physics will proceed with ruthless, textbook linearity. The Sun will expand, it will brighten, and it will envelope Mercury and Venus. Earth will sit on the precipice, likely spiraling inward due to tidal drag. The survival of Hala is a fluke of binary dynamics, a rare loophole that does not apply to single stars. We are looking at a miracle that cannot be replicated in our own backyard. It serves as a grim reminder that our safety is not guaranteed by the laws of physics, but rather endangered by them. Hala is the exception, Earth is the rule. The sheer timescale of these events is something that creates a sense of vertigo, a chronophobia induced by the vastness of deep time. The merger of the binary stars would have happened millions of years ago, a flash in the pan compared to the age of the galaxy. For millions of years since, Bectu has been burning helium quietly, masquerading as a normal star. The crime was committed eons ago, and the evidence has been slowly cooling ever since. We are detecting the anomaly only because we have built machines capable of freezing time, of catching the subtle wobbles and dips that betray the system's history. It makes you wonder what other violent histories are hidden in the calm, steady lights of the night sky. Every star you see could be the result of a merger, a collision, or a disruption, masking its trauma behind a facade of hydrostatic equilibrium. The sky is not a painting, it is a graveyard and a battlefield. We must also consider the chemical evidence found in the star's spectrum. Astronomers analyzing Bectu found an unusually high abundance of lithium. Lithium is a fragile element. It is easily destroyed by the intense heat and mixing currents inside a star. In a normal red giant, lithium should be almost non-existent, dredged up and burned away long ago. The presence of a lithium enrichment is often a sign of contamination, a sign that the star recently ingested something that contained lithium, like a planet or a brown dwarf. This data point supports the idea that the system was violent. Did Bectu eat a third body? Did the merger itself create fresh lithium through the Cameron-Fowler mechanism? Or is the lithium the last remains of the binary companion that was consumed? The star is literally belching the chemical signature of its victim. It is a stellar fingerprint that screams of ingestion and destruction. The second-generation hypothesis, the idea that Hala formed after the merger, requires a mental leap into the grotesque. Imagine the star Bectu expanding, destroying its original planetary system, pulverizing rock and gas into a swirling disk of superheated debris. This is a necrotic disk, a ring of death orbiting the star. Over millions of years, as the star stabilized into its helium-burning phase, this debris could have cooled and clumped together. Gravity acts as the ultimate recycler. From the ashes of the old worlds, a new gas giant begins to form, It accretes the gas that was stripped from its predecessors. It gathers the rocks that were once part of other mantles. In this scenario, Hala is a Frankenstein world, stitched together from the corpses of the first generation. It is a zombie planet in the most literal sense, dead matter brought back to life by gravity to orbit the star that killed it. If Hala is indeed a second-generation planet, it challenges the nebular hypothesis, which states that planets form only when the star forms. It suggests that planet formation is a recurring process, capable of happening at the end of a star's life just as easily as the beginning. This would mean that the universe is far more efficient at creating worlds than we thought. But what kind of world is created in such a hell? A planet formed from a post-red giant disk would be devoid of volatiles like water and methane initially, unless they were delivered later by comets. It would be a dry, dense metallic world, or a gas giant composed of heavier, processed elements. It would be a world born old, created from material that has already lived a full stellar lifetime. It is a disturbingly efficient use of cosmic waste. Let us look closely at the orbital mechanics again. The orbit of Hala is 93 days. This places it in a region where tidal interactions are incredibly strong. The gravity of the planet raises tides on the star, and the gravity of the star raises tides on the planet. This constant stretching and squeezing dissipates energy in the form of heat. For a planet this close to a giant star, this tidal heating could be significant enough to inflate the planet's radius, making it puffier than a normal Jupiter. If Hala is bloated, it becomes even more susceptible to stripping by the stellar wind. The planet is caught in a feedback loop. The closer it gets, the hotter it gets. The hotter it gets, the bigger it gets. The bigger it gets, the more drag it feels. It is a slow, grinding death spiral that takes eons to complete, but the outcome is mathematically inevitable. Hala is fighting a war of attrition against gravity, and gravity has infinite patience. The existence of Hala forces us to re-examine the great filter of the Fermi paradox. One of the reasons proposed for the silence of the universe is that planetary systems are unstable over long timescales. Life needs billions of years to evolve intelligence. If stars routinely eat their planets before intelligence can arise, or just as it is reaching maturity, then the universe is a hazardous place for civilization. Hala's survival suggests that some planets get a reprieve. But is a reprieve enough? Even if a planet survives the red giant expansion, the radiation environment changes drastically. The habitable zone moves outward. Any life on a planet like Hala or its moons would have been sterilized by the luminosity increase. Survival of the rock does not mean survival of the biosphere. Hala is likely a sterile monument, a tombstone orbiting in the silence. Consider the view from the surface of Hala. If one could stand on the swirling clouds of this gas giant, the star Baidu would span a massive portion of the sky, a seething wall of orange fire. The concept of sky would be meaningless. The star is the sky. The amount of stellar flux, the raw energy hitting the planet, is thousands of times greater than what Earth receives. The clouds would be made of exotic materials, perhaps silicates or vaporized metals, condensing in the upper atmosphere and raining down as liquid rock. It is a world of permanent incandescence, where the boundary between the planet's atmosphere and the star's corona is blurred. To survive here is to exist inside a furnace. It is a vision of hell that Dante could barely have imagined, verified by the cold, hard numbers of spectroscopy. The scientific term for the region where Hala exists is the post-main sequence desert. Statistics from the Kepler mission showed us that planets are rarely found in close orbits around evolved stars. They are usually swept clean, eaten, or pushed away. The fact that Hala sits right in the middle of this desert is why it is so disturbing. It's like finding a fish swimming in the middle of the Sahara. It implies that there are oases in the desert, specific configurations of mass and orbit that allow for survival against the odds. But these oases are rare, and finding one requires us to sift through thousands of dead systems. It makes Hala a precious specimen, a unique laboratory for testing the limits of planetary endurance. We must also consider the possibility of planetary engulfment, leaving a trace that we can see. When a star eats a planet, it spins up. The angular momentum of the planet is transferred to the star, making it rotate faster. Baekdu is rotating, but not at the breakneck speed we might expect if it had just eaten a Jupiter-sized world. This slow rotation is actually evidence against recent engulfment of a massive body, or evidence that the star has had time to slow down again via magnetic braking. Every piece of data is a clue in a temporal puzzle. The spin rate, the chemical composition, the seismic waves, they are all clocks running at different speeds, and our job is to synchronize them to find the moment the crime occurred. There is a deeper, more unsettling implication for the search for exomoons. If Hala is a gas giant, it likely formed with a retinue of moons, just like Jupiter and Saturn. But in this close orbit, the Hill sphere, the region where the planet's gravity dominates over the stars, shrinks dramatically. The moons would have been stripped away, pulled loose by the star's gravity, and sent careening into the void or crashing into the planet itself. Hala is almost certainly alone, a king without a court. The destruction of its moon system would have been a spectacular celestial fireworks display, a series of collisions that pulverize the satellites into a ring of dust that has long since dissipated. The silence of Hala is the silence of a lonely survivor who watched its family be torn away by the tide. The James Webb Space Telescope offers our best chance to confirm the merger hypothesis versus the survival hypothesis. By taking a spectrum of the planet's atmosphere, we could look for isotopic ratios of carbon and oxygen. A planet formed from the debris of a merger would have a different chemical signature than a planet formed from a primordial nebula. We are on the verge of being able to taste the air of this zombie world from 520 light-years away. If we find the ashes of a dead star in the clouds of Hala, we will know the truth. We will know that worlds can be built from the graveyards of stars. It is a grim archaeology, digging through the spectral lines for the bones of the past. Let us speculate on the future. What happens next? Baekdu is currently burning helium, but that fuel is finite. In roughly 100 million years, the helium will run out. The core will contract again, carbon and oxygen will build up, and the star will ascend the asymptotic giant branch. It will swell once more, becoming even larger and more luminous than before. This second expansion is the final death knell. There is no binary partner left to merge with. That card has already been played. There is no mechanism to stop the expansion this time. Hala's luck will run out. The star will expand beyond 0.5 astronomical units, and this time, the planet will be engulfed. The story of Hala is a tragedy in 2 acts, and we are watching the intermission. The final act is fire. The inevitable destruction of Hala serves as a memento mori for the cosmos. It reminds us that stable is a relative term. A system can be stable for 1 billion years and then vanish in a cosmic instant. The universe is a dynamic, evolving beast, shedding its skin and eating its young. We cling to the idea of permanence because our lives are so short. But to the galaxy, planets are fleeting, temporary condensations of matter. They form, they orbit, they are eaten. The cycle is ruthless and efficient. Hala's resistance is heroic, but futile. It is fighting a battle against thermodynamics, and thermodynamics never loses. However, until that final day comes, Hala remains a beacon of the impossible. Its existence challenges us to keep looking, to keep questioning our models. If we had stopped looking because we know red giants eat planets, we never would have found it. It proves that the universe is full of black swan events, rare, unpredictable occurrences that carry extreme impact. In the search for extraterrestrial life, these black swans might be the most important discoveries. Maybe life doesn't exist on the quiet, safe worlds. Maybe it clings to the edges of disaster, on the moons of zombie planets, in the shadows of dying stars. We have to look in the places we are afraid to look. The study of 8 Ursae Minoris b is also a triumph of the citizen science era in some respects, as the vast amounts of data from tests are open to the public. While the confirmation came from professionals, the initial signals are often hidden in datasets that anyone can download. It implies that the next great discovery, the next impossible planet, might be sitting on a hard drive right now, waiting for someone to notice the pattern. The sheer volume of data we are collecting is overwhelming. We are drinking from a fire hose of starlight. Who knows what other monsters are swimming in that stream, unnoticed by our algorithms? The universe is shouting its secrets at us, and we are just learning how to parse the language. Let's visualize the Roche-Loeb overflow in the binary merger scenario again, but with a focus on the visuals. As the primary star expands, it becomes teardrop-shaped, its material streaming towards the companion like a river of fire. This stream impacts the companion, creating a hot spot, a blindingly bright point of impact. The companion eventually spirals in, plowing through the outer layers, creating a shockwave that ripples through the entire star. This is a violent, turbulent event that would outshine the rest of the galaxy in specific wavelengths for a brief time. And sitting in the distance, safe in the cold dark, was Hala. Witnessing the grandest light show in the history of its system, the sky would have been lit up by the death of a star and the birth of a monster. The forbidden nature of this planet also has implications for our definitions of planetary types. We have hot Jupiters, super-Earths, and mini-Neptunes. Hala represents a new class, the post-engulfment survivor, or zombie Jupiter. We need a new taxonomy for these worlds that exist in the red zones of stellar evolution. Naming things is the first step to understanding them. By classifying Hala, we acknowledge that it is not a mistake in the data, but a feature of the universe. It legitimizes the study of these dangerous orbits and encourages astronomers to hunt for more. We are building a bestiary of the bizarre, and Hala is the first specimen in the exhibit of the undead. The density of Hala is another puzzle piece. Based on its radius and mass, it appears to be a typical gas giant, not a dense rocky core. This is surprising. If it had lost its atmosphere during the red giant phase, it should be smaller and denser. The fact that it retains its puffiness suggests that the stripping mechanism was not efficient, or that the merger happened very quickly. It implies that the common envelope phase was short-lived, a quick plunge rather than a slow roast. The speed of the event saved the planet's atmosphere. It's the difference between walking through a fire quickly and standing in it. Hala ran through the fire and came out singed, but whole. There is a terrifying quietness to the concept of the zone of avoidance. In galactic astronomy, this usually refers to the area blocked by the Milky Way's dust. In planetary science, it refers to the region close to a star where planets shouldn't be. Hala is squatting in the zone of avoidance. It is like finding a squatter in a condemned building that is scheduled for demolition. It defies the zoning laws of astrophysics. This defiance is what makes it scary in a scientific sense. It represents a variable we didn't account for, a force we didn't model. And if there is one variable we missed, there could be others. The equations we use to predict the safety of our own world might have similar blind spots. We must also consider the tidal decay timeline. Even though Hala survived the expansion, it is now orbiting in a region where tidal forces are constantly sapping its orbital energy. Calculations suggest that the timescale for tidal decay for a planet of this mass at this distance is on the order of billions of years, unless the star is evolved. Evolved stars have large convective envelopes that are very efficient at dissipating tidal energy. This means Hala should be spiraling in fast. The fact that it hasn't fallen in yet suggests that either we are catching it at the very end of its life, or the tidal dissipation inside the star is weaker than we think. We might be watching the planet in its final death throes, a few million years before the end. The light from Hala takes 520 years to reach us. This means we are seeing the system as it was during the Renaissance on Earth. In the grand scheme of the universe, this is a live feed. But physically, the information is always delayed. If Hala plunged into the star yesterday, we wouldn't know for another 5 centuries. We are always disconnected from the now of the universe. We are historians of the present, reconstructing events that have already happened. This lag adds to the ghostly nature of the study. We can never truly know the current state of 8 Ursae Minoris b. We can only know its past. For all we know, the catastrophe has already occurred, and the light of the planet's death is currently traveling across the void towards us. The comparison to other systems is vital. Take the system Kepler-56, which has 2 planets in tilted orbits around a red giant. Those planets are doomed. They will be eaten soon. Or the planet WD 1856b, a Jupiter-sized world orbiting a white dwarf, a star that has already died and shed its layers. WD 1856b proves that planets can survive the entire death process and end up orbiting the corpse of the star. Hala is the middle chapter between Kepler 56, the before, and WD 1856b, the after. It gives us the complete narrative arc of planetary survival. It proves that the journey from red giant victim to white dwarf survivor is possible, though fraught with peril. But WD 1856b is in a distant orbit. Hala is close. That is the critical difference. Survival at a distance is easy. Survival at point-blank range is the anomaly. It forces us to think about migration. Did Hala form further out and move in? If so, when? Migration usually happens early in a system's life, through interaction with the protoplanetary disk. Migration late in life is rare, requiring a gravitational kick from another massive body. If Hala migrated in after the star became a giant, it would be like running into a burning building. Why would a planet do that? The dynamics required to push a planet inward at precisely the right moment are complex and unlikely, making the in situ survival theory or the merger theory the only viable options. The cosmic horror aspect lies in the indifference of the process. The star Baekdu does not care about Hala. It expands according to the laws of nuclear fusion. The planet orbits according to the laws of gravity. There is no intent, no malice, just blind forces interacting on a massive scale. Yet, the result looks like a struggle. We project our own fears of mortality onto these celestial bodies. We see the star as a monster and the planet as a victim. But in reality, they are just matter converting energy. The horror comes from the realization that we are also just matter, subject to the same indifferent laws. Our sun will expand, our oceans will boil, and the universe will not shed a tear. Let's focus on the star's name, Baekdu. Named after the highest mountain on the Korean peninsula, a dormant volcano. The name is fitting. A volcano is a sleeping giant that can wake up and destroy its surroundings. The star is a cosmic volcano that has already erupted once and is preparing to erupt again. The planet Hala, named after the highest mountain in South Korea, sits in the shadow of this volcano. The nomenclature chosen by astronomers reflects the relationship. A majestic peak standing firm against a backdrop of geological, or in this case, astrophysical, violence. Even our names for these objects carry the weight of their precarious existence. The burning of helium in the core of Baekdu is a process that creates carbon and oxygen. These are the building blocks of life as we know it. The very atoms that make up our bodies were forged in the cores of stars like this one. It is a beautiful irony that the process which creates the elements of life is the same process that destroys the planets where life could exist. We are made of star stuff, but the stars are not our friends. They are factories that consume their own infrastructure. Hala is witnessing the production of the next generation of life's ingredients. But it pays the price by being bathed in the lethal radiation of the factory floor. What would the solar wind sound like on Hala? If the planet has a magnetic field, the interaction with the stellar wind would create auroras that cover the entire planet. Not just wispy curtains of green light like on Earth, but raging storms of ultraviolet and X-ray fluorescence. The sky would scream with electrical activity. The magnetic field lines would snap and reconnect, releasing bursts of energy that would fry any electronics we sent there. It is a planet wrapped in a permanent electrical storm, a shield of plasma trying to hold back the tide of the star's atmosphere. The visual spectacle would be blinding, a constant reminder of the invisible war between the planet's core and the star's wind. The zombie metaphor is overused in pop culture, but in astronomy it fits perfectly here. A zombie is something that should be dead but is moving. Hala fits the description. But there is another layer, the vampire star. In binary systems, the star that strips mass from its companion is often called a vampire. If Baekdu is a merger product, it is a vampire star that eventually ate its victim whole. So we have a zombie planet orbiting a vampire star. It sounds like a B-movie script, but it is the physical reality of the Ursa Minor system. The universe is writing horror fiction with gravity and plasma. As we look at the test light curve again, notice the precision. The dip is consistent, repeatable. This regularity is what anchors us. Amidst all the speculation about mergers, engulfment, and destruction, the clockwork of the orbit remains. Tick, tock. Every 93 days. It is the heartbeat of the survivor. It tells us that despite the chaos, order can emerge. But it is a fragile order. It is the order of a spinning top teetering on the edge of a table. We are watching it spin, mesmerized, waiting for the moment it falls. The suspense of the Hubble system is not if it will end, but when, and until then, it spins. The investigation into Hubble is far from over. New papers are being written. New models are being run. Some astronomers are trying to prove the merger theory wrong, trying to find a way for a single star to save the planet. Others are looking for the debris of the lost moons. Science is a battlefield of ideas, and Hubble is the contested territory. Every new observation is a potential bombshell. We are in the golden age of exoplanet discovery, where the outliers are teaching us more than the standard cases. Hubble is the professor in this classroom, and the lesson is that we should expect the unexpected. Let's consider the anthropic principle for a moment. We are here to observe Hubble because our planet survived. If Earth had been eaten, we wouldn't be here to wonder about it. So there is a selection bias. But Hubble isn't observing us. It is a dead world, likely. It represents the alternative path. The path where things go wrong, but not completely wrong. It is the bad ending of a video game that didn't quite result in a game over, just a corrupted save file. It exists in a state of limbo. Viewing it makes us appreciate the boring stability of our own solar system. Boring is good. Boring is safe. Exciting is Hubble, and exciting is terrifying. The red clump stars, like Big Dew, are standard candles in astronomy. We use them to measure distances across the galaxy. They are supposed to be well-behaved, predictable objects. Finding a planet like Hubble around one is like finding a glitch in a ruler. It makes us question the tool itself. If red clump stars can have hidden merger histories that alter their size and brightness, does that affect our distance measurements to other galaxies? The ripples of this discovery spread outward, affecting cosmology and the large-scale structure of the universe. A single zombie planet can cast a shadow that reaches the edge of the observable cosmos. We are 50 scenes away from the end of this script, and yet the mystery only deepens. We have established the crime, the planet exists, the suspect, the binary merger, and the weapon, gravity. But the motive, the why of the universe, remains elusive. Why does nature permit these configurations? Is it purely random, or is there a strange attractor in the mathematics of system formation that favors survival? Perhaps planets are harder to kill than we think. Perhaps they are stubborn, clinging to their orbits like barnacles on a whale. The resilience of matter against the void is the underlying theme of this cosmic tragedy. Imagine the sound of the binary merger again. In space, there is no sound, but there are gravitational waves. The collision of two stars would send ripples through the fabric of space-time, a chirp that LIGO could detect if it happened today. We missed the chirp of LIGO's merger by millions of years. But the echoes are there in the orbit of Hubble. The planet is riding the wake of that gravitational tsunami. It is surfing on the distortions left behind by the cataclysm. In a way, the planet is a gravitational wave detector, its orbit tuned to the frequency of the destruction that birthed its current reality. The hot Jupiter problem has always been about migration. How do they get so close? Hubble adds the survival problem. How do they stay there when the star grows? It combines two of the biggest headaches in planetary science into one object. It is a migraine for theorists. But migraines are symptoms of deeper issues. The issue here is our incomplete understanding of angular momentum transfer. We don't really know how efficient viscosity is in a star. We are guessing at the stickiness of plasma. Hubble is telling us that plasma might be less sticky or gravity more forgiving than our code assumes. We need to rewrite the code. As we look at the star Big Dew, remember that it is a K-type giant. It is cooler than the Sun but far larger. Its surface gravity is lower. This means its atmosphere is fluffy, extended. Hubble is orbiting through the outer fringes of this fluff. It is like an airplane flying through the top of a thunderhead. The drag is low, but constant. It is this constant, subtle drag that will eventually seal the planet's fate. It is not a sudden collision, but a slow suffocation. The planet is wading through the ghost of the star, and the ghost is dragging it down. The visual isolation of the planet in our simulations is stark. We usually show exoplanets with dramatic lighting, lens flares, and dramatic music. But the reality is a silent, dark sphere against a blinding background. The contrast is too high for the human eye to resolve. If you looked at Beidou, you would go blind instantly. You wouldn't see Hubble. It is lost in the glare. We only know it's there because of the math. The math is our eyes. It allows us to see into the blinding light and find the shadow hiding within. Ephemeris matching is the technical term for predicting where the planet will be. We have an ephemeris for Hubble. We know where it will be next week, next year, next century. This predictability is comforting. But if the period starts to change, if we see a period decay, that will be the signal that the end has begun. We are watching the clock, waiting for it to lose a second. The moment Hubble arrives a minute late for its transit, we will know that the spiral has started. It will be the countdown to extinction, broadcast live across the galaxy. There is a theory that Hubble might not be a planet at all, but a dense knot of stellar material, a stellar core fragment. This is highly unlikely, but in the realm of the impossible, we must check every door. If the merger was violent enough, could a piece of the core have been ejected and stabilized? No, the physics doesn't support it. It would explode or evaporate. Hubble is definitely a planet, a gas giant, a survivor. The simplest explanation, that it is a planet, is the most terrifying because it forces us to accept the survival scenario. We cannot explain it away as a stellar chunk. It is a world. The habitable zone of Beidou is currently far out, beyond the orbit of Hubble. If there are other planets in this system, perhaps further out at 2 or 3 astronomical units, they might be enjoying a pleasant climate right now. The red giant phase warms up the outer system. Frozen worlds like Europa or Pluto would melt and become ocean worlds. Hubble is the sacrifice in the center that creates the warmth for the outer system. It is the fuel for the fire that warms the rest of the house. Is there life watching from a distant moon, thankful for the giant star, unaware of the tragedy happening at 0.46 astronomical units? The sheer power of the helium flash that Beidou underwent cannot be overstated. It is a nuclear bomb the size of a star going off in the core. For a few hours, the core produces more energy than the rest of the Milky Way combined. But this energy is absorbed by the star's layers, causing it to ring. Hubble felt this. The gravitational shockwave of the flash would have jerked the planet in its orbit. It rode out the biggest explosion in the local universe and kept going. It is a bunker planet, built to withstand stellar apocalypse. What does the future hold for our understanding of Hubble? The test mission has been extended. We will get more data. We will refine the orbit, but the real breakthrough will come from understanding binary evolution. We need to simulate millions of binary mergers to see how often a Hubble is produced. If the simulations say never, then we are missing physics. If they say sometimes, then we have solved it. We are currently in the simulating phase, running the universe in a box to see if we can break it in the same way nature did. The philosophical weight of Hubble is heavy. It tells us that the universe is not designed for us, or for planets. It is a chaotic arena where things happen because they can, not because they should. The should is a human invention. Hubble shouldn't exist, but it does. Therefore, our should is wrong. We must align our philosophy with the reality of the zombie planet. Existence is a struggle, and survival is a glitch. We are all just glitches in the thermodynamic decay of the universe. As we move into the final phase of this script, we will look at the ultimate implications. What does Hubble teach us about the end of the Earth? Is there any hope for us to survive the sun's expansion? Can we move the Earth? Can we engineer a survival like Hubble's? The answer lies in the physics of orbital dynamics and the limits of engineering. Hubble did it by accident. Can we do it on purpose? The forbidden planet might be the blueprint for our own salvation, or the tombstone of our future. Let us find out. To truly grasp the magnitude of the discovery of Hubble, we must first appreciate the staggering difficulty of finding it in the first place. The planet itself emits no light of its own. It is a dark, cold ember orbiting a blazing bonfire. We cannot simply point a telescope at 8 Ursae Minoris and take a photograph of the planet. The glare of the star Beidou is millions of times brighter than the faint reflection of the planet. washing out any direct visual data. Instead, astronomers rely on the radial velocity method, a technique that detects the subtle gravitational influence of the planet on the star. As Hala swings around in its orbit, its gravity tugs on the star, causing Baekdu to wobble back and forth in space. This wobble is infinitesimal, a shift in the star's movement that is slower than a human sprinting, yet it causes the light from the star to stretch and compress, shifting towards the red and then the blue end of the spectrum. This Doppler shift is the heartbeat we are listening for, a rhythmic pulse in the light that tells us, without a shadow of a doubt, that something massive is lurking in the glare. It is a ghost, detected only by the footprints it leaves in the light of its host. The classification of Hala as a hot Jupiter places it in a category of planets that has baffled scientists since the first exoplanets were discovered. In our own solar system, the gas giants are far away from the Sun, in the frozen outer reaches where volatile gases can condense. But hot Jupiters orbit dangerously close to their stars, often completing a year in just a few days. The standard theory is that these planets formed further out and then migrated inward, plowing through the primordial disk of gas and dust until they park themselves in a fiery orbit. But Hala adds a new layer of complexity to this migration model. If it migrated inward billions of years ago, it should have been consumed when the star expanded. If it migrated inward recently, after the expansion, what force pushed it? Planetary migration requires a medium to interact with, a disk of gas to create drag. But the disk around Baekdu dissipated billions of years ago. This leaves us with the unsettling conclusion that Hala might have been pushed by a gravitational kick from another body, a violent game of cosmic billiards that sent it careening towards the star just as the star was shrinking. We often speak of the Rosetta Stone, the artifact that allowed us to decipher ancient Egyptian hieroglyphs. In astronomy, Hala is a Rosetta Stone for the language of stellar death. Before this discovery, we assumed that the expansion of a red giant was a simple monotonic sentence. The star grows, the planet dies. Hala translates a more complex dialect of physics, one where binary interactions, mass transfer, and orbital resonances create a grammar of survival that we are only just beginning to learn. It tells us that the exclusion zones we have drawn on our maps of the galaxy are not rigid borders but permeable frontiers. The existence of this planet forces us to go back and reread the data from thousands of other stars, looking for the subtle signs of survival we might have missed because we were too arrogant to believe they could exist. It effectively unlocks a new chapter in the book of the universe, one titled Life After Death. Now, we must pivot the camera from the distant constellation of Ursa Minor and point it directly at our own chest. The story of Hala is not just a curiosity, it is a forecast. In approximately 5 billion years, our own Sun, a G-type main sequence star, will exhaust the hydrogen in its core. The hydrostatic equilibrium that has kept our planet safe for 4 billion years will shatter. The core will contract, heat up, and the outer atmosphere of the Sun will begin to expand. This is not a hypothesis, it is a certainty of nuclear physics. The Sun will swell into a red giant, its radius growing until it swallows the orbits of Mercury and Venus. The sky of Earth will change from a comforting blue to a blinding, wall-to-wall sheet of red fire. The oceans will boil, the atmosphere will be stripped away, and the surface of our world will return to the molten state of its infancy. The question Hala poses is, will the expansion stop there, or will the Earth be consumed? The mechanics of Earth's potential engulfment are a grim study in tidal forces and drag. As the Sun expands, it will lose mass through a potent solar wind which weakens its gravitational grip on the Earth. This mass loss should, in theory, cause Earth's orbit to widen, allowing it to spiral outward and stay just ahead of the expanding photosphere. It is a cosmic race, the Sun growing outward versus the Earth retreating outward. However, there is a counterforce, tidal drag. The Sun's rotation will slow down, and the tidal bulge raised by Earth on the Sun will lag behind, creating a gravitational brake that steals energy from Earth's orbit. If the tidal forces win, Earth will not escape. It will be dragged inward into the solar atmosphere. Once inside, the density of the gas will act like a thick fog, slowing the planet down until it spirals into the core. Hala survived this drag. Earth, being much less massive than Jupiter, will likely not be so lucky. The mass difference between Hala and Earth is the critical variable in this survival equation. Hala is a gas giant, hundreds of times more massive than Earth. This mass gives it immense momentum, allowing it to plow through the tenuous outer layers of a star without losing too much speed. It is like a bowling ball rolling through fog. Earth, by comparison, is a ping-pong ball. If Earth enters the solar atmosphere, the drag forces will be overwhelming. The friction will heat the planet to thousands of degrees, melting the crust and vaporizing the rock. We will not survive inside the star. We will dissolve. Hala's survival is likely due to its sheer bulk, a brute force resistance against the stellar wind. This implies that in the end, size matters. The giants might survive the apocalypse, but the small, rocky worlds, the ones that harbor life, are the first to be erased. This terrifying future has led scientists and futurists to propose the concept of planetary engineering. If we know the sun is going to expand, and we know Earth's natural retreat won't be fast enough, could we move the planet ourselves? It sounds like science fiction, but the physics is sound. We would not use giant rockets strapped to the South Pole. That would crush the crust and atmosphere. Instead, we could use gravity assists. By steering a large asteroid or comet to swing close to Earth, we can transfer a tiny bit of orbital energy from the asteroid to the planet. The asteroid slows down, and Earth speeds up, moving into a slightly wider orbit. If we repeat this process thousands of times over millions of years, we could slowly spiral Earth outward, keeping it in the habitable zone as the sun expands. We could effectively turn our planet into a spaceship, fleeing the death of our star. However, the gravity tractor method of moving Earth requires a level of coordination and longevity that humanity has never demonstrated. We would need to manage the orbits of thousands of asteroids for millions of years, without a single mistake. One miscalculation could send an asteroid crashing into Earth, causing the very extinction we are trying to avoid. Furthermore, as we move Earth outward, we disrupt the orbits of Mars and Jupiter, potentially destabilizing the entire solar system. It is a delicate game of celestial Jenga. Hala suggests that nature can move planets, either through scattering or migration, but the result is often a chaotic, lonely orbit. If we move Earth, we might save the rock, but the biosphere would be stressed to the breaking point. We would be refugees on a drifting raft, sailing away from the only warmth we have ever known, into the cold darkness of the outer solar system. The psychological impact of living under a dying star is something we can scarcely imagine, yet it is the reality for any hypothetical observer in the Hala system. On Earth, the sun is a constant, a benevolent god that dictates our days and seasons. But as a star turns into a red giant, it becomes a monster. It grows brighter and redder, changing the color of the sky, the photosynthesis of plants, and the temperature of the oceans. For a civilization on a planet like Hala, if one existed on a moon, the end of the world would not be a sudden event, but a slow, creeping realization that the sky is eating the horizon. It would be a multi-generational trauma, a slow-motion apocalypse visible to the naked eye every single day. The survival of the planet Hala is physically impressive, but the environment it survives in is a psychological nightmare of heat, radiation, and impending doom. Returning to the classification of Hala, we must ask, what is it made of now? A gas giant that survives close to a star is not the same planet it was when it formed. The intense heat of the star causes the atmosphere to puff up, increasing its radius but lowering its density. Simultaneously, the high-energy ultraviolet radiation from the star smashes into the molecules in the upper atmosphere, breaking them apart and giving them enough energy to escape the planet's gravity. This process, called photoevaporation, means that Hala is slowly leaking its atmosphere into space. It is bleeding gas. Over millions of years, this could strip away the entire hydrogen envelope, leaving behind the naked, molten core. Hala is currently a gas giant, but it is in the process of becoming a Chthonian planet, a dead core that remembers it was once a giant. The concept of a Chthonian planet is named after the Greek deities of the underworld, the infernal gods. It is a fitting name. These are worlds that have been stripped of their outer beauty, their clouds and storms revealing the superheated, pressurized rock beneath. If Hala survives the next phase of Baekdu's expansion, it might end up as one of these underworld planets. It would be a diamond and iron ball, orbiting a white dwarf. The pressure at the core of a gas giant is high enough to turn carbon into crystal. So in a way, the death of Hala as a gas giant is the birth of Hala as a diamond world. It is a transformation through fire, a cosmic alchemy that turns gas into precious stone, but at the cost of the planet's soul. The magnetic connection between Baekdu and Hala is another invisible tether that binds their fates. Stars have magnetic fields, and planets have magnetic fields. When they are this close, the fields interact, creating a magnetic flux tube that connects the two bodies. Massive electrical currents, billions of amps strong, flow between the star and the planet. This current heats the planet's upper atmosphere, causing it to glow in the ultraviolet. It also creates a hotspot on the surface of the star, a permanent magnetic footprint where the planet is tethered. Hala is not just orbiting the star, it is plugged into it. It is drawing energy from the star and dumping energy back into it. They are a coupled system, a single electrical circuit spanning 40 million miles of vacuum. The isolation of space is a theme we keep returning to because it is the defining characteristic of the Hala system. In our solar system, we have neighbors. We can see Mars, Jupiter, Saturn. We have sent probes to them. We feel part of a family. Hala is an orphan. The data suggests no other large planets exist in the system. The binary merger, or the expansion, likely cleared them out. To look up from Hala is to see the blinding star on one side and the absolute, crushing blackness of deep space on the other. There are no other wandering stars to mark the passage of time. It is a solitary confinement cell in the galactic prison. This profound loneliness accentuates the horror of its situation. Trapped with a dying beast, with no one to hear the scream. We must interpret Hala through the lens of the Great Filter. This is the idea that there is some barrier that prevents life from becoming a galaxy-spanning civilization. Usually we think of the filter as nuclear war, or climate change, or the difficulty of abiogenesis. But Hala suggests the filter might be the stars themselves. If planetary systems are unstable, if stars routinely eat their children, then long-term stability is the rarity. Perhaps civilizations arise frequently, but they are incinerated when their stars turn on them. Hala is a survivor of the filter, but it is a sterile survivor. It suggests that the universe is good at making rocks and gas, but very bad at keeping them safe long enough for those rocks to start thinking. The James Webb Space Telescope, JWST, is our primary tool for unlocking the next level of this mystery. Unlike TESS, which detects the presence of the planet, JWST can sniff its atmosphere. By watching the planet pass in front of the star, JWST can analyze the starlight filtering through the planet's rim. The molecules in the atmosphere, water, methane, carbon dioxide, perhaps even isotopic markers of the star's interior, will absorb specific wavelengths of light. This transmission spectroscopy will tell us if Hala is made of primordial material or if it is polluted with the ashes of the star. It is a remote autopsy of a living world. We are waiting for the telescope to turn its gold-plated eye toward Ursa Minor and tell us what the zombie is breathing. The lithium mystery deserves a second look because it is the most damning piece of chemical evidence we have. Lithium is created in the Big Bang and is consumed in stars. It should not be abundant in an old star like Baekdu. Its presence is like finding a fresh flower in a fossil bed. It implies a recent event that created or injected lithium. The merger of two helium-core white dwarfs could do it. The ingestion of a massive planet could do it. The fact that Baekdu is lithium-rich marks it as a deviant star. It carries the chemical brand of a violent past. Hala orbits a star that is chemically marked as a cannibal or a merger product. The very light that shines on the planet carries the spectral lines of a crime scene. We have to remember that binary stars are the norm, not the exception. About 85% of stars exist in binary or multiple systems. The Sun, being single, is actually the weird one. This means that the drama playing out at 8 Ursae Minoris, the merger, the common envelope, the survival, might be a very common story in the universe. We might be the outliers living in a quiet, boring house, while the rest of the galaxy lives in a war zone of merging stars and disrupted orbits. If binary mergers are common, then zombie planets like Hala might outnumber normal planets like Jupiter. We might be living in a galaxy populated by survivors of stellar trauma, and we are just now noticing them because we finally looked in the right place. The universe is often described as a clockwork mechanism, precise and orderly. But Hala proves it is more like a biological ecosystem, messy, competitive, and cannibalistic. Stars eat planets, stars eat other stars, galaxies eat other galaxies. It is a food chain of gravity. Hala is currently the prey that got away, but it is still swimming in the shark tank. This biological metaphor shifts our perspective from physics to survival. We are not studying inanimate objects. We are studying the winners and losers of a cosmic struggle for mass and angular momentum. Hala is a winner for now, but in this game, winning just means dying last. Time is the ultimate distortion in this study. When we look at Hala, we are looking into the deep past of the star's evolution. But we are also looking at the future of our own system. It is a time machine in two directions. It shows us what happened to Baekdu millions of years ago, and it shows us what will happen to the Sun billions of years from now. This duality is what makes astronomy so poignant. We are studying our own mortality by looking at the ghosts of others. Every data point from Hala is a memento mori, a reminder that everything we know is temporary. The planet is a mirror reflecting the inevitable fire that awaits us all. There is a fringe hypothesis that we must address, if only to dismiss it. The simulation hypothesis. If the universe is a simulation, anomalies like Hala could be considered rendering errors or edge cases, where the procedural generation of the cosmos glitched. While this is philosophical rather than scientific, the impossible nature of the planet does feel like a bug in the code. Why would the laws of physics allow a planet to exist inside the radius of a star? It feels like clipping through a wall in a video game, but the reality is likely that our code, our understanding of physics, is what is buggy, not the universe itself. The universe is always right. It is our textbooks that are wrong. The Goldilocks zone, the region where liquid water can exist, is a moving target. Around a red giant like Baekdu, the habitable zone moves outward to where Jupiter or Saturn would be. Hala is far inside the roasting zone, but if there were icy moons orbiting Hala, which we believe were stripped, they might have melted into ocean worlds for a brief few million years as the star expanded. This creates the tantalizing possibility of transient life. Life that springs up during the death throes of a star, flourishes for a cosmic blink of an eye, and is then extinguished when the star collapses or expands again. It is a fleeting, tragic bloom of biology in the face of apocalypse. When a planet does get eaten, it creates a red nova. This is a specific type of stellar explosion that is redder and dimmer than a supernova. We have observed these events in other galaxies. V838 Monocerotis is a famous example, likely a merger event. If Hala eventually falls into Baekdu, it will trigger a red nova. The star will brighten, puff up, and turn a deep blood red. It will be a signal flare announcing the death of the planet. Any civilization watching from 520 light-years away will see a sudden spike in the light curve and know that the survivor has finally fallen. It is the funeral pyre of a world, broadcast at the speed of light. Let's revisit the necrotic disk theory, the idea of second-generation planets, because it is the most metal concept in astronomy. A star dies, destroys its planets, creates a disk of death, and new planets form from the corpse dust. If Hala is one of these, it implies that planets are resilient ideas. You can destroy the body, but the gravity reforms. It creates a cycle of reincarnation. But these second-gen planets would be weird. They would be metal-rich, dry, perhaps devoid of the lighter gases. They are the undead of the planetary family. Studying Hala's composition could prove this. If it has high metallicity matching the star's core, it is a child of the ashes. Visualize the binary system before the merger. Two stars, whirling around each other, distorting into teardrop shapes due to gravity. This is called a contact binary, or W Ursae Majoris variable. They touch. They share an atmosphere. It is a stellar kiss of death. Hala would have orbited this double yolk star. The light in the sky would have been a bizarre, shifting intensity as the two stars eclipsed each other every few hours. Living on such a world, or its moons, would mean having a strobe light for a sun. The stability of Hala's current orbit is a stark contrast to the chaotic disco of its past. There is a distinction between rogue planets, wandering the void, and Hala. Rogue planets are lonely but safe from fire. Hala is not lonely, it has the star, but it is in mortal danger. Which is worse, to freeze in the dark or to burn in the light? Hala chose the fire. Or rather, gravity chose for it. The existence of Hala suggests that safe orbits are a luxury. Most of the mass in the universe is probably in these dangerous, marginal configurations, or lost in the void. We on Earth are the pampered aristocracy of the galaxy, unaware of the hard life led by the 99% of planets. We have listened for radio signals from 8 Ursae Minoris. The Green Bank Telescope and others have swept the area. The result, unsurprisingly, is silence. Hala is not broadcasting. It is a dead rock. But the silence is heavy. It forces us to confront the fact that intelligence is likely rare. If Hala had a civilization, they had millions of years to see the red giant coming. Did they leave? Did they migrate? Or did they succumb to the apathy of the inevitable? The silence of Hala is a blank canvas onto which we project our own fears of extinction. Hala is a monument to the concept of hysteresis, the dependence of the state of a system on its history. You cannot understand Hala just by looking at its current position. You need to know where it was. Physics is usually time reversible, but stellar evolution is not. You cannot unburn helium, you cannot unmerge stars. Hala is a trapped piece of history. It carries the memory of the system's path. It is a physical manifestation of the arrow of time, pointing relentlessly towards entropy. Entropy is the villain of this story. The second law of thermodynamics dictates that disorder must increase. A star burning fuel increases entropy. A planet spiraling in increases entropy. Hala's survival is a temporary eddy in the river of entropy, a small pocket of order that has refused to dissolve yet. But the river always wins. The star will burn out. The planet will fall or freeze. The universe is a machine for destroying structure, and Hala is just a particularly stubborn piece of structure. The second wind of the star, the phase after the merger, is what Hala is enjoying now. The star is stable, burning helium. This is the calm after the storm, but it is a deceptive calm. The fuel is running out. The star is consuming itself from the inside. When the helium is gone, the carbon core will contract, and the outer layers will pulse again. This thermal pulsing is the death rattle. Hala is sitting next to a patient in hospice who has rallied for one last day of clarity before the end. It is a poignant, tragic pause in the process of dying. The ultimate fate of Baekdu is to become a white dwarf, a small, dense, Earth-sized crystal of carbon and oxygen slowly cooling over trillions of years. Will Hala still be there? If it survives the second expansion, it will orbit this dim ghost forever. The view from Hala would change from a sky full of fire to a sky with a single, piercingly bright blue dot. The planet would freeze. The atmosphere would rain out as nitrogen snow. It would become an ice giant guarding a dead star. This is the good ending. The bad ending is vaporization. We have found a planet around a white dwarf before, WD 1856b. That discovery proved that planets can make it to the end. But WD 1856b is far away from its star. Hala is the test case for close-range survival. If Hala makes it to the white dwarf phase, it will be the ultimate survivor. It will have been inside a star, blasted by a merger, roasted by a giant, and frozen by a dwarf. It would be the most battle-hardened object in the galaxy. We should name it the Iron Planet, not for its composition, but for its will. If Hala is a carbon-rich planet, which is possible if it accreted material from the carbon-rich interior of the red giant, the pressure physics are fascinating. Deep inside, carbon doesn't just compress, it changes phase. We could be talking about a planet with a mantle of liquid diamond, raining diamond hail in its deep interior. The sky is raining diamonds sounds like a fairy tale, but on gas giants like Uranus and Neptune, and potentially Hala, it is just weather. A weather forecast of heavy diamond precipitation is a stark reminder of how alien these worlds are. The atmosphere of Hala is likely filled with silicate clouds, clouds of rock. On Earth, water evaporates and rains. On Hala, rock evaporates and rains. Imagine a storm where the droplets are molten lava or jagged glass shards. The winds, driven by the heat of the star, would whip this glass rain around the planet at supersonic speeds. It is a reign of terror. To be exposed on the surface, if there was one, would be to be sandblasted into oblivion in seconds. It is a world of violent, abrasive beauty. The wind speeds on hot Jupiters are calculated to be thousands of miles per hour, a super-rotating jet stream that circles the planet. This jet stream redistributes the heat from the day side to the night side. But on Hala, the heat is so intense that even the night side glows red. There is no darkness on Hala, only shades of burning. The wind is not a breeze, it is a shockwave that never ends. It is a planet screaming into the void, its voice the roar of a continuous, global hurricane. Tidal locking is the nightmare scenario for habitability. One side cooks, one side freezes. But on Hala, the cooking side is facing a red giant. The temperatures are likely over 1000 Kelvin. The freezing side is facing space but is warmed by the winds. The Terminator line, the border between day and night, would be the only place with complex weather. It is a twilight zone of eternal sunset, where the red sun sits on the horizon forever, casting long, terrified shadows across the cloud tops. We project our humanity onto these rocks. We call them lonely, terrified, survivors. But Hala is just gas and gravity. The terror is ours. We are afraid of the dark. We are afraid of the fire. Hala is a mirror for our existential dread. We look at it and see our own fragility. We see how easily the universe could wipe us out. The planet is not the horror. The realization of our own insignificance is the horror. Hala is just the messenger. Yet, the human instinct to explore is driven by this dread. We want to know if we can survive. We study Hala to find a loophole in the contract of death. If a ball of gas can cheat the Reaper, maybe we can too. We are looking for a precedent for survival. Every paper published on 8 Ursae Minoris B is a prayer for salvation, written in the language of calculus. We are begging the universe to tell us that the end is not inevitable. The Fermi paradox asks, where is everybody? Hala answers, they are dead. Or, they are hiding. If environments like this are common, then intelligent life must be incredibly robust to survive. We might be the soft, squishy exceptions in a galaxy of diamond-hard survivors. The aliens we eventually meet, if any, might not be biological. They might be machines, or post-biological entities that have abandoned their fragile homeworlds to live in the void. Hala suggests that staying at home is a death sentence. This strengthens the rare Earth hypothesis. The specific conditions that allow for a long-term, stable, habitable planet might be winning a cosmic lottery. We need a single star, not binary, a stable orbit, no giant migration, no nearby supernovae. Hala shows us what the standard chaotic system looks like. It makes Earth look like a paradise, a protected garden in a war zone. We should not take our boredom for granted. Our boring sun is the greatest gift we have. But could there be super-habitable worlds around red giants? For a brief time, the frozen outer planets become warm, a greenhouse age on a Pluto-like world. Civilization could rise in the twilight of a star, flourishing in the warmth of the giant, only to die when the star collapses. It would be a civilization with a known expiration date, a culture obsessed with the inevitable end. They would look at their giant red sun not as a giver of life, but as a ticking bomb. Consider the ice moon of Enceladus in our system. It has an ocean under the ice. If the sun expanded, that ice would melt. Enceladus would become a water world. For a few million years, it would be a paradise. Then the water would boil off. Hala might have had such moons. We are looking at the dried-out husk of a system that might have had its own brief golden age before the fire came. We missed the party by 1 billion years. We are just walking through the ruins. The constellations we see in the sky are temporary. Ursa Minor, the little bear, will not look like a bear in 1 million years. The stars are moving. Baek Du is moving. In the future, the forbidden planet will be in a different part of the sky, or the system will be dead. We are drawing pictures in the sand while the tide comes in. The story of Hala is a snapshot of a moment in a constantly shifting kaleidoscope. Nothing stays still, nothing stays the same. The mythology of the little bear involves Arcus, the son of Zeus, turned into a bear to protect him. It is a story of transformation and protection. How fitting that the star 8 Ursae Minoris holds a planet that was protected from destruction by a miraculous transformation of its star. We weave stories into the stars, and sometimes the science matches the myth. The universe has a sense of poetry, even if it is a dark, ironic poetry. Polaris, the North Star, is also an Ursa Minor. It is our guide. But 8 Ursae Minoris is the warning. One star guides us home. The other tells us that home is not safe. They are the twin pillars of our galactic neighborhood, hope and dread. We need both. We need to know where we are going, and we need to know what to avoid. Hala is the lighthouse on the rocks, warning us of the dangers of stellar evolution. As we navigate the final leg of the script, we must prepare to leave Hala, but we cannot unsee it. Once you know that zombie planets exist, you look at every point of light differently. You wonder what drama is playing out around that speck of light. Is there a planet screaming in the fire? Is there a world watching its sun die? The night sky becomes a theater of tragedy. It is no longer a peaceful canopy. It is a violent, churning, deep ocean full of monsters. The legacy of Hala will be written in the textbooks of the future. It will be cited as the anomaly that broke the models. The Baekdu anomaly. It will inspire a generation of astronomers to look for the impossible. It teaches us that the word impossible in science usually just means we haven't seen it yet. The universe is wider than our imagination and stranger than our equations. We are closing in on the end. The final scenes will bring us back to Earth, to the ultimate question. What do we do with this knowledge? Do we panic? Do we despair? Or do we build better ships? Hala tells us that survival is possible against the odds. It is a call to action. If a dumb rock can survive a red giant, surely a smart species can figure something out. The end of the world is a concept we grapple with in religion and fiction. Hala is the scientific version of the end times. It is the revelation of St. John written in hydrogen and helium. It shows us the lake of fire. It shows us the new heaven and the new earth, or the old earth reborn. It is eschatology for astrophysicists. We stand on the shoulders of giants to see these things, Kepler, Newton, Einstein, but they never saw Hala. We are the first generation of humans to know that this planet exists. We are the privileged witnesses to this cosmic miracle. It is a heavy burden, this knowledge. It separates us from our ancestors who looked at the stars and saw only gods. We see mechanics, we see fire, we see truth. Now, let us turn our eyes away from the ghost planet and look at the future. The real horror is not what happened to Hala, but what will happen to us. The clock is ticking for Earth. The investigation of the alien world is over. The investigation of our own fate begins now. We return now to the Sol system, our home, to apply the grim lessons of Hala to our own future. We often speak of the sun's death as a distant, abstract event, something that belongs to the realm of deep time, irrelevant to human history. But the process has already begun. The sun is getting brighter by about 10% every billion years. This is not a fluctuation. It is a linear ramp-up of nuclear efficiency. Long before the sun becomes a red giant, this increased luminosity will trigger a runaway greenhouse effect on Earth. The oceans will evaporate, filling the atmosphere with steam, which is a potent greenhouse gas. This will trap more heat, causing more evaporation, in a lethal feedback loop. The surface temperature will soar to hundreds of degrees. Earth will become a second Venus. This is not a possibility. It is a thermodynamic inevitability. Hala's survival is a story of surviving the fire. Our story will be about surviving the steam. Imagine the sky of this future Earth, roughly 1 billion years from now. The sun is not yet a giant, but it is uncomfortably bright, a searing white eye that punishes the surface. The continents are barren, stripped of vegetation by the heat. The oceans are gone, leaving behind vast salt flats and canyons of dried mud. Life, if it still exists, has retreated underground, into the crust, seeking the cool dark. We will have become a subterranean species, hiding from the star that gave us life. The story of Hala gives us false hope. We look at it and think, planets can survive. But Hala is a gas giant. It has no surface to scorch, no oceans to boil. For a rocky world like Earth, survival means remaining a rock, but the biosphere, the living skin of the planet, is far more fragile than the geology. The crucial difference between the Hala system and the solar system is the lack of a binary companion. Bagdu had a partner to merge with, a sacrificial lamb that halted the expansion. The Sun is alone. There is no second star to strip away its envelope, no gravitational partner to initiate a common envelope phase. The Sun's expansion will be unchecked, a solitary ballooning into the void. This single-star status, which currently provides us with such a stable environment, becomes our death warrant in the end phase. We have no mechanism to stop the red giant. We are locked in a car with no brakes, heading towards a cliff, and unlike Hala, there is no one in the passenger seat to pull the emergency brake. Our isolation is total. This realization forces us to confront the concept of stellar husbandry or starlifting. If nature won't save us, can we save ourselves? Physicists have proposed megastructures that could theoretically strip mass from the Sun, extending its life and preventing it from becoming a red giant. By using magnetic fields to lift plasma off the solar surface, we could reduce the mass of the star, keeping it in the main sequence for longer. It would be the ultimate engineering project, performing surgery on a star to keep it from dying. We would have to dismantle the very thing that sustains us. It is a scale of engineering that borders on godhood, but Hala tells us the alternative is being eaten. We either master the stars, or we are consumed by them. But what if we cannot stop the Sun? The alternative is to leave. The generation ship concept imagines a vessel that travels between stars, carrying a population of humans who will live and die in transit. Hala teaches us that planets are not safe harbors. They are temporary rafts. To truly survive the cosmos, we must become a spacefaring civilization, independent of any single gravity well. We must become the aliens that science fiction writers dream of, nomads of the void, moving from star to star, harvesting energy and resources before moving on. The survival of the species depends on decoupling our fate from the fate of the Earth. We must divorce our mother planet to save the children. The transition from a planetary species to a stellar species is the great filter step that we are facing. Most civilizations probably don't make it. They stay on their rock, distracted by internal conflicts, until the star expands and erases them. Hala is the tombstone of a system that didn't have space travel. If there was life there, it died screaming. The silence of 8 Ursae Minoris is a warning. Do not stay too long. We are currently in the womb of the biosphere, but eventually, we must be born into the cold, harsh universe. Birth is painful and risky, but the alternative is death in the womb. Let us look at the habitable zone of the future. As the Sun expands, the zone where liquid water can exist will move outward to the moons of Jupiter and Saturn, Europa, Ganymede, Enceladus, Titan. These frozen worlds will melt. For a few 100 million years, the solar system will have a new golden age in the outer rim. Humanity could migrate to these new ocean worlds. Imagine cities floating on the seas of Europa, watching the giant red sun loom over Jupiter. It would be a second genesis for human civilization, a retreat to the suburbs of the solar system as the city center burns. But even the outer planets are not safe forever. The red giant phase is unstable. The Sun will pulse, throwing off shells of gas. These pulses could strip the atmospheres of the moons, or sterilize them with radiation. The refuge is temporary. This is the recurring theme of the cosmos. There is no permanent safe house. Every shelter is temporary. Every sanctuary has an expiration date. We are refugees running from a fire that burns slowly but never stops. The universe is a hostile landlord that eventually evicts everyone. The visual of the planetary nebula that the Sun will eventually create is hauntingly beautiful. The gas shed by the dying star will be ionized by the remaining core, glowing in vibrant colors of red, blue, and green. It will be a stunning celestial flower blooming in the dark. But at the center of that flower will be the charred cinder of Earth. Aliens looking at our system 5 billion years from now will see a beautiful nebula and marvel at its structure, unaware that it is the grave of a civilization. Beauty in astronomy is often the aftermath of violence. There is a theory called panspermia, which suggests that life can be spread between stars by rocks and dust. If Earth is destroyed, debris carrying microbial life could be ejected into interstellar space. These arcs of rock could drift for eons until they land on a young planet, seeding it with the building blocks of Earth biology. In this way, Earth could survive not as a planet, but as a genetic legacy. We might be the ancestors of life across the galaxy, our death spawning 1,000 new beginnings. It is a comforting thought that our information survives even if our hardware is destroyed. However, this relies on the resilience of DNA. Halla suggests that physical survival is possible, but biological survival is the hard part. The radiation environment of a post-main sequence system is lethal to complex molecules. DNA breaks down. Proteins denature. The only thing that might survive is information encoded in something more durable than flesh. This brings us to the post-biological future. If we want to survive the death of the sun, we might have to stop being biological. We might have to upload our consciousness into machines, into silica and metal that can withstand the vacuum and the radiation. A machine civilization could thrive around a star like Baekdu. They could harvest the energy of the red giant, use the high metallicity of the system to build structures, and live in the vacuum of space. To a machine, Halla is not a hellscape. It is a power plant. The zombie planet might actually be a bustling industrial hub for a robotic species that doesn't care about oxygen or temperature. We project our biological frailties onto the universe, but the universe might belong to the machines. Halla might be the ideal real estate for the next stage of evolution. The concept of the Dyson sphere involves building a shell around a star to capture all its energy. A civilization advanced enough to do this would not fear a red giant. They would control it. They would modulate the star's output. They would be the masters of the stellar life cycle. We are currently at type 0.7 on the Kardashev scale. We control a fraction of our planet's energy. To survive the sun, we need to reach type 2, control of the star. Halla is a reminder of the raw power we need to tame. It is a challenge issued by the cosmos. Level up or die. Let us zoom out to the galactic scale again. The Milky Way is colliding with the Andromeda galaxy in about 4.5 billion years. This coincides roughly with the death of the sun. So just as our star is expanding to kill us, the sky will be filled with the collision of two galaxies. It will be a time of absolute chaos. Stars will be flung out of their orbits. The night sky will be a swirl of new star formation and merging black holes. It is the grand finale of our local cosmic neighborhood. Halla is just a small prelude to this symphonic destruction. In the face of such overwhelming forces, nihilism is a tempting response. Why bother? Why build cities and write symphonies if it all ends in fire? But the existence of Halla offers a counter-argument: resilience. The planet shouldn't exist, but it does. It fought the odds. It represents the stubborn refusal of matter to be erased. We share that stubbornness. It is encoded in our genes. We survive ice ages, plagues, wars, and volcanoes. Surviving a star is just the next logical step in our history of defying the odds. The black hole era of the universe lies far in the future, long after the stars have burned out. All that will remain are black holes and Hawking radiation. Halla will be long gone by then, its protons decayed, its matter dissipated. But for this brief, shining moment in the stelliferous era, the age of stars, we are here. We are conscious, we are watching. The universe has created a way to look at itself, and we are the eyes. To look away from the horror of Halla is to deny our purpose. We are the witnesses of the cosmos. We have spoken of cosmic horror, but there is also cosmic awe. The two are sides of the same coin. The scale that terrifies us is the same scale that elevates us. When we look at the image of the star field around Ursa Minor, we are looking at infinity. It crushes our ego, but it expands our mind. We are small, yes, but we are capable of understanding the immense. That is our superpower. We can hold the death of a star inside our heads. We can model the apocalypse in our computers. We are the universe understanding itself. The final legacy of Halla might be to jumpstart our search for techno-signatures. If we accept that biological life is fragile, we should stop looking for water and start looking for waste heat, for industrial pollution, for the signs of machines moving planets. A civilization that survived a red giant would leave a mark. They would have to. We should scan 8 Ursae Minoris not just for natural radio waves, but for the artificial hum of a planetary shield generator. We might find that the zombie is actually a bunker. But until we find those signals, we are alone. The silence is the loudest thing in the universe. It screams at us. It tells us that we are responsible for our own survival. No one is coming to save us. No friendly aliens are going to tow Earth to a safe orbit. We have to do it. The story of Hala is a call to maturity for the human species. It says, grow up. The universe is dangerous. Start preparing. We are currently building the next generation of telescopes, the Extremely Large Telescope, ELT, the Giant Magellan Telescope. These eyes on the ground will be able to see the atmospheres of Earth-sized planets. We will soon know if there are other Earths out there, but finding another Earth doesn't save this one. It just tells us where to run. And running is hard. Interstellar travel is the hardest physics problem we have ever encountered. We are trapped by the speed of light, imprisoned by the vast distances. The paradox of Hala is that it is a dead world that feels alive because of its story. We have anthropomorphized a ball of gas because we need a protagonist in the dark. But the real protagonist is gravity. Gravity is the hero and the villain. It formed the star. It merged the binary. It pulled the planet. It holds the atmosphere. Gravity is the sculptor of the universe, and we are just the clay. Hala is a masterpiece of gravitational sculpture, shaped by violence and time. Let us imagine the final moments of Hala, whenever they come. As the star expands for the second time, the drag will increase. The planet will spiral in. The atmosphere will heat up until it glows white. The planet will become a second star for a brief moment, rivaling Baidu in brightness. Then, it will dissolve. The material will be mixed into the star. The lithium abundance will spike again. The star will burp, and then settle down. It will be a silent, bright end. No fanfare. Just physics. This dissolution is a form of unity. The planet returns to the star that made it, ashes to ashes, dust to dust. In astrophysics, it is gas to gas, plasma to plasma. The separate identity of the planet is lost, but the matter remains. The atoms that made up Hala will eventually be blown out into the galaxy as the star dies. They will form new nebulae, new stars, new planets. The cycle continues. Hala will die, but its atoms will live on to build new worlds. This cyclic nature of the universe is the closest thing we have to immortality. We are part of a process that has no beginning and no end. The Big Bang was a moment, but the churning of matter is eternal. We are waves in the ocean. Hala is a wave that held its shape for a little longer than the others, but it will eventually crash back into the water. We should not mourn the wave. We should admire the ocean. The overview effect is what astronauts feel when they see Earth from space, a sense of fragility and unity. Studying Hala gives us a galactic overview effect. We see our solar system from the perspective of deep time. We see how fragile our entire home is. It makes our petty wars and politics seem insanely trivial. We are fighting over seats on the Titanic while the iceberg is looming. Hala tells us to look at the iceberg. The data from Hala is stored in servers on Earth, silicon chips holding the secrets of a dying star. If humanity falls, this data will be lost. The memory of Hala will vanish. The universe does not keep records. We do. We are the librarians of the cosmos. If we die, the library burns. This is why we must survive. Not just for ourselves, but for the knowledge we have gathered. To let the story of Hala be forgotten would be a second death for that world. As we near the end of this script, the feeling should not be despair, but urgency. We have time. 5 billion years is a long time. We have evolved from stone tools to space telescopes in 10,000 years. Imagine what we can do in a billion. We can move planets. We can tame stars. We can rewrite the laws of nature. The potential of humanity is infinite if we don't destroy ourselves first. The forbidden planet is a challenge to our ingenuity. The light from Baidu is streaming towards us right now. Photons created in the core of a giant, bouncing through the radiative zone, crossing the vacuum, hitting our detectors. It is a physical connection. We are touching the star with our eyes. This connection binds us to the cosmos. We are not separate from the universe. We are an integral part of it. We are the way the universe knows itself. There is a mystery that remains. Why is the orbit circular? Even with the merger, even with the survival, the circularity is weird. It implies a settling time that the timeline doesn't seemingly allow. Perhaps gravity works differently on these scales. Perhaps modified Newtonian dynamics, MOND, plays a role. Hala is a pebble in the shoe of general relativity. It irritates the theory, and irritation leads to progress. We will keep watching 8 Ursae Minoris. We will watch it for decades, centuries. We will pass this vigil on to our children. Watch the zombie planet. Tell us if it blinks. It is a multi-generational science project. It connects us to the future observers who will know more than we do. We are the pioneers, stumbling in the dark, mapping the coast of a new continent. The constellation Ursa Minor contains the North Star, the anchor of our navigation. It is ironic that the same constellation holds the anchor of our existential dread. One star tells us where we are, the other tells us where we are going, to dust. They are the alpha and omega of the sky, navigation and annihilation. The sky is a map of human destiny, if we know how to read it. What if Hala is just the first of thousands? What if the test data is full of them, and we just need to filter the noise better? We might be on the verge of a population explosion of zombie planets. This would change our understanding of the galaxy from a collection of stable systems to a collection of survivors, a galaxy of PTSD. It reframes the Milky Way as a violent, dangerous place where safety is the exception. The Drake equation calculates the number of civilizations. We need to add a term for planetary survival rate. Hala helps us define that variable. It is not 100%, it is not 0%. It is somewhere in the messy middle. That messy middle is where we live. We are navigating the probabilities, trying to stay on the right side of the decimal point. The beauty of the visual prompts we have used, the moon, the earth, the stars, reminds us that these are all just shapes of the same matter. The moon is a rock, earth is a wet rock, the sun is a hot gas. Hala is a hot gas. We are thinking matter. It is all one substance, rearranging itself. The tragedy of Hala is just a rearrangement. A sad one, but a natural one. If we could send a probe to Hala, it would take millions of years to get there. By the time it arrived, humanity might be gone. The probe would be a message in a bottle from a dead civilization to a dying planet. We were here. We saw you. There is a poetic futility in interstellar exploration. But we do it anyway. Because the act of reaching out matters more than the arrival. The colors of the Hala system would be alien. An orange sky, black clouds, red shadows. Our eyes evolved for a yellow sun. We would see Hala as a nightmare, but to a creature evolved there, Earth would look blue and cold and sickly. Normal is a local definition. The universe has no normal. It has only variety. As we wrap up, think of the astronaut looking back at Earth, that iconic image. Now imagine the astronaut looking at Hala. A black disk against a wall of fire. That is the image of the future. That is the destination of all matter. To be consumed. We are fighting a rearguard action against the dark. And for now, we are winning. The Forbidden Planet is a title we gave it. Nature forbids nothing. Nature permits everything that is physically possible. Our surprise is a measure of our ignorance. Hala is a teacher. A harsh, hot, distant teacher. It tells us to open our minds to the bizarre, to expect the impossible, to never say never to the universe. We have peeled back the layers of 8 Ursae Minoris b. We found a survivor, we found a merger, we found a mystery. But the core of the mystery is still untouched. The why of existence remains. Why does the universe bother to create such complexity only to destroy it? Perhaps the creation is the point. The dance is the purpose, not the ending. Hala is dancing with Baekdu, a dangerous tango. They spin together in the dark. We are watching from the balcony, holding our breath. The music is gravity. The lights are starlight. And the dance goes on. It goes on until the music stops. And for Hala, the music is slowing down. The final takeaway is this. Reality is scarier than fiction because it is relentless. Fiction has narrative logic, it has heroes, it has happy endings. Reality has physics. Physics doesn't care about your story. It cares about mass, energy, and momentum. Hala is a story written by physics, and it is the best, most terrifying story we have ever heard. We are the universe's way of feeling fear, and awe, and wonder. Without us, Hala is just a rock. With us, it is a tragedy. We give the universe meaning. We are the storytellers. And this script is our attempt to give meaning to a distant, dying world. We have witnessed it. We have named it. We have remembered it. So, the next time you look at the North Star, look a little to the side. Look at the darkness where 8 Ursae Minoris hides. Send a thought to the zombie planet. Acknowledge its struggle. It is your brother in the fight against entropy. It is holding the line. It is surviving. And so are we. The universe is vast, cold, and empty. But it is also full of surprises. Hala is the surprise in the cereal box of the cosmos. A deadly, radioactive surprise, but a surprise nonetheless. It keeps us looking. It keeps us dreaming. It keeps us afraid. And fear is a powerful motivator. We are done with the investigation. The file on Hala is closed, but not sealed. We will return. We always return. To the scene of the crime. To the edge of the cliff. To the forbidden planet. Because we cannot help ourselves. We are explorers. We are human. This is the lead scriptwriter signing off. The story of the planet that shouldn't be real is now yours. Use it to scare them. Use it to inspire them. Use it to remind them that the ground beneath their feet is temporary. Everything is temporary. Even this video. Even this script. But the idea of Hala will last. The idea that something can survive the fire. That is an immortal idea. It is the spark of hope in the darkness. Hold on to that spark. It is the only thing that keeps the cold away. The screen fades to black. The music swells. The credits roll. But the planet keeps spinning, 520 light-years away. In the silence. Alone. Reality is scarier than fiction. Remember that. Look up. Be afraid. Be amazed. Be alive. End of transmission.